Section 1.4, Inductive Reasoning. Now, the objectives for this section is first, to use inductive reasoning to identify patterns and make predictions based on data. The second objective is to use inductive reasoning to provide evidence that conjectures are true or provide counterexamples to disprove them. Definitions. So an inductive...
Stop. Say that again because you have to wait till it's read.
Oh, I see. Now on to the definitions. An inductive reasoning is a type of reasoning that reaches conclusions based on patterns of specific examples or past events. A conjecture is an unproven statement or rule that is based on inductive reasoning. A counterexample is an example that shows a statement or a conjecture is false. Here's a diagram for an overview of this topic. From patterns, we can make generalizations, and from the generalizations, we can make the conjectures. Now, we will use inductive reasoning to extend a pattern. So how can we use inductive reasoning to determine what appears to be the next two terms in each sequence? So here's the first example. We have 800, 400, 200, and 100. Now, each of these are called the terms. And 800 is our first term, 400 is our second, 200 is our third, and then 100 is our fourth. With the patterns that we will solve out, we will also find the fifth and sixth. So how do we get from 800 to 400? Well, we could see that we can divide it by 2. And that's how we got 400. How about from 400 to 200? We also divided by 2. Then from 200, from 100 was also divided by 2. So for our fifth term, we will divide 100 by 2, which will become 50. And if we continue our pattern, from the fifth term, we will divide that by 2 and we'll get 25. So now we can see that our fifth and sixth pattern is 50 and 25. Okay, on to our second example. Here we have 3, 5, 9, 15, and 23. Now, if we look at the pattern from 3 to 5, we see that we have to add by 2. From 5 to 9, we had to add by 4. And from 9 to 15, we had to add by 6. And from 15 to 23, we have to add by 8. And as we can see from this pattern, it was multiples of 2. So 2, 4, 6, 8. And therefore, from that, we can make a generalization that the next couple of terms will be added by other multiples of 2. And the next 2 is 10 and 12. So from 23, we have to add by 10. And we'll have 33. And then from 33, we have to add by 12. And that will become 45. So with that pattern, we got the fifth and sixth term, which is 33 and 45.
This example is use inductive reasoning to make a conjecture. What conjecture can be made about the number of dots in the nth term of this geometric pattern? So the first term, we have 1 dot. And the second term, we have 3 dots. And in the third term, we have 6. And it's growing like a pyramid, like a triangle. This is the fourth term. This is the fifth term. And we want to figure out how many dots are in the sixth term. So we'll pause the video right now for you to think about that. Okay, so what do you think? Like, if you talk to your partner about this, how is this growing? How many dots are on the bottom of the sixth term? That's right, there's going to be 6, because in the fifth term, there were 5 dots on the bottom. And then above those 6 dots that are on the bottom, we will have 5 dots. And then it's going to grow like a pattern. So above the 5 dots, we have 4 dots. And above that, we have 3 dots, 2 dots, 1 dot. So how many would that be? It's going to be 6 plus 5 plus 4 plus 3 plus 2 plus 1. And if we add those, 11, 15, I'm getting 21. Just count again. 21. So that answers part A. There are 21 dots in the first pattern. Part B asks, what conjecture can you make about the number of dots in the nth term of the pattern? Well, if we look at this bottom piece, we have n dots. And then as we go up the pyramid, we're taking a dot away. It's counting backwards. So if you start with n, the next row up is going to be, you're going to add n take away 1. And then the next row up would be n take away 2. And you would have to do this as many times as there are n. So in that last problem, there were 6, it was the 6th term. So we would have to do each part of this 6 times. So we have 1, 2, 3, 4, 5, 6 times. This is not quite good enough for a generalization, and they came up with a formula that shows this pattern, and I don't want to spend too much time showing how that works, but if you use the method I just showed you, where you take the n's, and you could even simplify this, this would be for the 6th term. You could do the same thing for the 7th term, the 8th term, but it's time consuming. And so some genius came up with this generalization that always works. N squared plus n divided by 2. And we can check that. So for the 6th term, let's check that. We'll put 6 into n. 6 squared plus 6 divided by 2. That equals 36 plus 6 divided by 2. And if we come down here, that is going to be 42 divided by 2, which equals 21. So that checks that it works. And you can check it for the 5th term, you can check it for the 4th term, and now you could do the 100th term, and you wouldn't have to draw 100 dots, 99, 98, 97, 96, all the way up to the 1 dot at the top of the triangle. So this, I'm going to get the highlighter, is the general term for the nth term. And if you have a highlighter, you can highlight the titles of today's notes.
Now, we will use a conjecture to make a prediction. So based on the data, how many members would you expect the chess club to have in its 5th year? So in our first year, we had 10 members. In the second year, we had 13. In the third year, 17 members. Fourth, it's 22. So from the first year to the second year, there are 3 more members. And from the second to the third year, there are 4 more members. And here, from the third to the fourth, we have 5 more members. So for each one of the years passing, we added 1 more from the last. So on our 5th year, we could say that we will add 6, because that is 5 plus 1. So 22 members plus 6 will be 28. So on their 5th year of the chess club, they will have 28 members. Now we will find a counterexample to show a conjecture is false. What is a counterexample that shows that the statement, all fruits have seeds on the inside, is false? Now one I can think of for a counterexample is a strawberry. Now this is because a strawberry has seeds on the outside, and therefore this statement is false. Now, to test a conjecture. For each conjecture, test the conjecture with several more examples, or find a counterexample to disprove it. For part A, every integer n, the value of n squared is positive. Now, as we remember before, integers can be -1, -2, or any numbers in the number line from 5 to infinity. So if we take a square of one integer, that'll be, and that's a positive number. And if we take the square of a negative number, that will also be a positive number. However, if you remember, there is 0 on our number line. If we take the square of a 0, that will be a 0, and that is neither a positive or a negative. So this statement is false. Now for example B. A number is divisible by 4 if the last 2 digits are also divisible by 4. Divisible means it can be divided by 4. So it can be 12. It can also be 8. So if we had big numbers with those with 2 digits, the last 2 digits divisible by 4. And I have that solved out, and that would be 128. Now, you can take other ones too, like 1028. And you see this part, that's divisible by 4. And with quick calculator, that's equals to 257. So I would say that this statement is true. Any number with the last 2 digits divisible by 4 can be divided by 4. Okay, and now we will just go back to these problems, and we will say that for this statement on part A example is false. And for part B, this statement is true.